Thank you, Sarah, for doing a great introduction to data assimilation. So in terms of motivation for what we do and why we do it, this is a image from the World Meteorological Organization talking about information that's provided on different time scales, which is on the y-axis here, going from a few minutes where there's a lot of activity in terms of coordination, watches and alerts. For instance, the Hurricane Beryl, which was on the previous slide, there were watches and alerts, both for like tornado warnings, as well as like hurricane strength wind related damages, right? So that all happens when the event is really imminent and there's a lot of information, less uncertainty. The uncertainty that we are talking about is plotted in these orange lines, which only increases in time in terms of forecasts. And we'll come to why it increases in time in a few slides. So then as we go further along in time, we have forecasts, weather forecasts, which are issued on timescales of days. Further along, if we go to subseasonal to seasonal timescale, weeks to seasons, we get information in terms of assessments, threats. Is it going to be wetter than normal or drier than normal in the next month? Those are kind of information that are provided on subseasonal to seasonal timescale. And then we can go out all the way into seasonal to interannual, where ENSO plays a big role. Then climate change timescale, if you're talking about projections. So looking 100 years or 50 years from now, what is the projected scenarios that could occur depending on different decisions that are made? So all this information should come with what's called uncertainty. And there are different things that go into quantifying uncertainty. And on the x-axis here is the applications of information, right? So on the short time scales, you're talking about saving lives, property, and that uses information about warnings, watches, alerts, coordination. Going out further into subseasonal time scale, you have applications on water resource management, hydropower, agriculture. And then out onto the climate time scales, you're talking about environmental decisions or decisions about infrastructure that last for 50 years, maybe. So those are decisions that would take into account not only the forecast, but also uncertainty that accompanies a forecast. So we need both accurate forecasts, but accurate uncertainty accompanying these forecasts. So that's generally laying out the motivation for what is done operationally. In terms of learning goals for today's lecture, these are the learning goals that I've listed. So we learn why representing initial condition uncertainty is necessary in ensemble forecast. And this directly relates to what Sarah was talking about, data assimilation, which is essentially trying to give us the best initial condition for a forecast. And then we learn about the two main sources of uncertainty and how they impact ensemble forecasts. We learn how machine learning can augment traditional data assimilation that Sarah presented. We learn why we need stochastic parameterization, which is model error representation. And that represents uncertainty in our model itself. And then I'll finally give an example and we learn about how we can use machine learning for model uncertainty representation. So this is laying out a context for all of this. Why do we need this? We don't have a linear system, right? We have a nonlinear system, which is the Earth's atmosphere ocean. So there's a butterfly sitting on the stand. And the lawyer says, during this trial, we intend to prove that this butterfly, by negligently flapping its wings, set in motion a chain of events resulting in a tornado, making him financially responsible for the damage. So I'll give a little historical perspective and an example of what is the system we are solving and why does uncertainty play such a big role in terms of predicting this system. This is Ed Lawrence, who's a famous mathematician and a meteorologist. He was a faculty at MIT. He wrote this paper in 1963 called Deterministic Non-Periodic Flow, which is a very simple model. All of you probably have heard of this. It's famously called the butterfly model. It has just three equations, three variables. It's the simplest nonlinear system that can demonstrate chaos. And yeah, and these are the three equations essentially. So you have x, y, z, the three variables. There are nonlinear terms. X and z interact, x and y interact, and there are three constants as well, sigma, r, and b. And this model is essentially trying to simulate flow between two plates of different temperature. Right? It's a chaotic system, which essentially means small perturbations in the initial conditions can lead to large error growths. The error growth is not linear; it's non-linear. So here I show an example of what happens when we initialize the model at different states. I'm just plotting the x and z variable here. The y variable would be on the other axis, the third axis. The black dots here are showing climatological attractor space. So the model can take, or the system can take a value anywhere on this attractor space. So similar to our thinking of our climatological evolution of the atmosphere in this model, each of these black dots are a solution to those three equations, right? What I do here is take three different regimes. I call them predictable, semi-predictable, and unpredictable, and I'll come to why they are called so in a second. I take one value in these three different regimes of the attractor space. I sample 50 values around that single value. So you can think of that as an ensemble, which is 50 perturbations to that initial condition. And then I integrate that model forward in time. And I see how these 50 members diverge as we integrate the model forward in time. So what we see here is these 50 dots tend to stay close to one another for a long time. Here they're staying close to one another, and then eventually they start diverging. Here they pretty much start diverging from the get-go, from starting the model itself. What's plotted here is what's called the ensemble anomaly. It's the difference of each of these 50 members from the mean of them. So you take the mean of the 50 values and you compute the difference of each of them from that mean. That's plotted here in terms of the x variable. So the anomaly in x remains small, so it's predictable. Here, the anomaly grows in time. Initially, it's small, but eventually it grows. So that's showing that initially there is some predictability, or the uncertainty is less. Eventually, the uncertainty becomes large. And here, the uncertainty grows pretty much from when you start integrating the model. And this is seen even in the real world example. So these are ensemble forecasts of tropical cyclones or hurricanes in different basins. This one is Hurricane Haiyan, which brought a lot of damage in the Philippines and the maritime continent. What's plotted here is the probability from the European Center's model, where the blue colors indicate, blue and purple indicate high probability of the track of the hurricane. So from yesterday's talk, you would have learned about how probabilistic forecasts of tropical cyclones work. So here the model and all the ensembles stayed close in terms of, and they agreed in terms of where the track of the hurricane would be. This is for Katrina, where initially there was a less uncertainty, large probability of where Katrina would go, but then it could have hit anywhere along the Gulf Coast. And it brought a lot of damage in the New Orleans, Louisiana coast. And this one is another example of Hurricane Naveen, where the forecasts either said some of the ensemble members took the hurricane towards Spain, the others took it out into the open ocean. So the consequence for the society is very different in terms of this kind of uncertainty, right? So that's the kind of system we are thinking about. There is uncertainty when we integrate the model forward because of the chaotic nature of the system. So now let's have a discussion question on this. So which of the following statements is true regarding initial condition uncertainty and model error? So like I mentioned, initial condition is where you're starting the model and running it forward. The model error is where you have erroneous terms in your model. So if you for instance, if you take the Lorentz model, right? And here you have fixed values for R, sigma, and B. But let's say you don't know exactly what those values should be. So you have different values for R, sigma, and B. That can be a parameter error in the model. So that's kind of what we are dealing with the real world as well. The ocean model or the atmospheric model, we don't really know how exactly to parameterize some of the physics in the system. So if you think of that, which of the following statements is true regarding initial condition error and model error in ensemble forecasting? A, initial condition error primarily affects long-term forecasts, while model error primarily affects short-term forecasts. B, initial condition error primarily affects short-term forecasts, while model error primarily affects long-term forecasts. C, both of them equally affect short and long-term forecasts. And D, initial condition error only affects oceanic forecasts, while model error only affects atmospheric forecasts. B is the answer. Right? If you think about weather forecasts, they are very dependent on how you get the initial conditions accurately. But thinking about climate forecasts, for instance, if you're projecting at 10, 50 years from now, it doesn't matter what your initial conditions are. So if some of you have run climate models, you would see that climate models don't really do data assimilation, even though they should for deep ocean, for instance. But the deep ocean does influence long-term climate. But otherwise, climate models don't care about initializing exactly for today, because within like a couple of weeks, that information is lost in the system, right? Like the system does not remember exact initial conditions beyond a certain time. So the answer is B. So this brings us to the different types of uncertainties that influence model projections or model forecasts of the real world, of the Earth system. The first one is the initial condition uncertainty, where we want to reduce that as much as possible, which is done through data assimilation, which Sarah talked about today morning. So you want to collect all the observations you can. You want to have the best model you can of the system, and you want to combine both of them to give best forecast. You will never get the perfect initial conditions just because the system is what it is. You cannot represent infinite digits on your computer, for instance. You cannot get information about the Earth system everywhere all the time. There's a movie, right? Everything, always, everything. So that's not possible about the Earth system. So we will have initial condition uncertainty. And the model error is because we don't know the Earth system perfectly well. We know that there are physics in the system we are not representing. There are physics in the system that are misrepresented because of approximations. So that brings in model error in our weather and climate models. So now we'll learn more about a little bit more about initial condition uncertainty and data assimilation. And then we'll talk about stochastic parameterization. Just a brief introduction. So this is what Sarah showed. So we have A. In Sarah's example, this was a linear matrix propagating the system forward. In the real system, A is a nonlinear system. We have some model. It will be a function of X, so it will not be a matrix multiplication unless you're doing discretized matrix multiplication. But the true system, you have a set of differential equations propagating the system forward, and you have associated covariance propagating forward. And then here you have the data assimilation where you have the model forecast. So the weather or climate model is stepping forward in time, giving you the state, and you get observations, which is, so this term is also called as innovation, which is observation minus your model forecast. So you have observation at a certain time, you have the first guess from the model. E is essentially transporting the model state to the observation state. So it can also be called as an observation operator, which tells you how the observations would have looked like if you observe the model. So for instance, if you have a satellite and you have a satellite simulator, which is simulating the real satellite in the world, the satellite simulator would take profiles in your model and that would tell what the model observation should have looked like. That is EX, and then Y is your real world observation. So you can take a difference to tell how they are different, right? Because you cannot, your observations are not necessarily the model state itself. For instance, the satellite simulator is looking at radiance, whereas the observation for the satellite and the observation is radiance, whereas your model state variable may not be radiance, it's temperature, for instance. So you have to convert temperature to radiance to compute that difference. So that's what is happening here. And then you combine that information with the model forecast to give you the best estimate or the best initial condition for your next forecast. And then in terms of model error representation, there's just one cartoon. I'll come back to this later. But the model error representation is done through what's called as stochastic perturbation. So you have some initial condition with uncertainty associated with them. Typically, that's represented in the ensemble forecast, where you have many different initial conditions that are sampling your distribution at the initial time. And then you have your forecast model, but we know that the forecast model is uncertain. So we have different representations of the forecast model. It might be either multi-physics, so you have different physics equations for the same parameterization, so you can do that and have different models. Or it could be what's known as stochastic parameterization, where you add random perturbations to your model physics terms. So that random perturbation will also give you different representations of your forecast model. So that will propagate the initial condition uncertainty forward in time to give you the forecast uncertainty, which will be a combination of model error as well as initial condition error. What do we want as an output from this? What we typically want is called as a reliable ensemble forecast. So by reliable ensemble forecast, what I mean is that it provides a realistic estimate of the uncertainty in the forecast. So that's central both to the school, but also to the whole forecast industry, right? Like we want both the forecast, but also an accurate estimate of the uncertainty in the forecast. That's what is mathematically or statistically qualified as reliability in the system, that the PDF that comes out of such a system accurately represents the PDF of the real world. So let's do another discussion question on this. So in ensemble forecasting, what are the main implications of an under-dispersive ensemble? So how many of you know what under-dispersive means? So under-dispersive means that the ensemble is not dispersing enough, right? Like the ensembles are close to one another rather than being far apart. So what are the implications of something like that? So A, this leads to overconfident predictions, underestimating variability and the risk of underestimating the risk of extremes. B, it gives an accurate range and conservative predictions. It equally is reliable as what is called as over-dispersive. So over-dispersive is where the ensemble spreads out too much. Then D is broader range, less certain predictions. So how many of you say A? Okay, almost everyone. How many of you say B, C, D? Yeah, you're right. And yeah, so this is like a cartoon representation of this. So in a reliable ensemble, the ensemble spread is a predictor of the ensemble error. So let's say the blue dots are your ensemble prediction, right? Like, for instance, I had 50 ensemble members forecasting the Lorentz system. So all of them at certain time have some value. And your observation is this white dot in the middle. Oh, no, sorry. The ensemble mean is the white dot, sorry. And the observation is the red dot. What you want is the observation to be somewhere within your ensemble spread. And this error, so the error is given by the standard deviation of your ensemble from the ensemble mean. So that sigma x should predict what's the error in your forecast. So epsilon x is the observation minus the ensemble mean. So that's the error in your forecast. If sigma x accurately predicts this, then it's called a reliable ensemble. Because when you're doing the forecast, you don't have red. Red is like a post facto information, right? Like it comes in after you do the forecast. For instance, if you're doing the forecast of the hurricane tomorrow, you don't know what the observation is, but you can get uncertainty based on the ensemble spread that you're integrating forward. So if that spread is accurately representing the error, that means the observation is indistinguishable from one of the ensemble members. Whereas if you have an under-dispersive ensemble where all the members are close to one another, but far from the observation, then you're too confident in the forecast, and the error is much larger than the spread in the system. The over-dispersive case is the opposite, where you have a broad ensemble spread. Here, the error is small, but you don't know how accurate your ensemble is, because they're so far spread out that the error is actually an overestimate of this ensemble spread is an overestimate of the error in the system. So both of these are bad. What we want is a reliable ensemble where your ensemble spread is an accurate representation of the error in your forecast. Okay, so I'll try to go through a couple of examples now on the machine learning part. I'll not dive deep into the machine learning itself, but I'm happy to chat about that later on. It's hard to cover everything, but I thought laying the foundations would be useful for now. Yeah, so in terms of the European Center, the initial condition uncertainty comes in both from the ensemble data assimilation framework, where your ensemble assimilates observations and you get that P matrix that Sarah talked about, which represents ensemble uncertainty in the initial conditions. And they also do what's called as singular vectors. I'll not go in depth into this, but that's essentially projecting onto the error growing modes in the system. So singular vectors are, you can think of it as EOFs, but they're not exactly EOFs, but they're directions in which the error grows the most in a chaotic system. And then the model uncertainty is represented through this stochastic perturbation, which maybe I'll touch upon later given time. So now I'll jump into the machine learning part, coming back to these equations. So we have the model, we have the covariance, we have the Kalman gain matrix. And what Sarah talked about is the Kalman filter without the ensemble framework. What is typically done in operational centers is they use the ensemble model to provide the P matrix. So to generate P from the model, which is high dimension, like 1 million grid points, so the matrix would be too high dimensional to propagate forward the P matrix. But what is typically done is you run an order of 100 ensembles, and you can show mathematically that the covariance across this ensemble represents the model covariance P, which is what is used when you're doing operational ensemble data assimilation. And that's where nonlinearity comes into play as well. Like Sean was asking, the model ensemble is propagating forward the nonlinear equations, so that covariance that you get at the end of the ensemble provides like the nonlinearity in terms of the evolution. So there are two different approaches. One is the smoother or the 4D variational trajectories, and you can run an ensemble of them. And that gives you some uncertainty when you assimilate observations into the system. The yellow here is giving you the first guess, which is without any assimilation, what's the uncertainty when you integrate the ensemble forward. So when you assimilate observations, your uncertainty becomes more accurate, that you're closer to the observations and a better representation of uncertainty. And then you can initialize the model from here and then run the ensemble forward again to get the next first guess. Okay. But this has challenges even in terms of operational prediction. Some of the bottlenecks are we need ensembles or multiple model runs to get this. Even in the variational approach, you run the tangent, linear, and adjoint model multiple times in a loop to converge the cost function J. So that is computationally expensive. Model space to observation space mapping, which is that E matrix or the observation operator, that can also be computationally challenging. Due to different reasons. Then you have the challenge of inverting very large matrices. So if you think of the Kalman gain matrix K, you have that inverse of a matrix, right? And that can be computationally very expensive if you have a large dimensional matrix. And then also computing gradients in this very large dimensional space is challenging because you're computing gradients and descending along that gradient to get to the minima. And that can also be challenging. So what a student of mine, Lucas, tried was to emulate this whole thing with a machine learning approach. So due to those computationally challenging issues, there are large quantities of observations that are not assimilated into the model. For instance, an example is like there's a satellite that measures satellite radiance globally, but only about 0.01% of the observations the satellite gets is actually assimilated into the weather forecast model. So there's like billions of dollars that go into launching the satellite, but only 0.01% of that data is actually being ingested into the system, right? And then like recently there was an ocean satellite, SWOT, that was launched that observes like sub-mesoscale scales in the ocean, but it's very hard to assimilate something like this into our ocean models because of the data quantity and having to massage the data, manipulate the data to ingest it into the model. So what Luke tried was to use machine learning to emulate some of this. Once the machine learning model is trained, it becomes computationally much cheaper to do this. So previously, people have done different approaches to bring in machine learning into data assimilation. I will not go into all of this. I will only talk about emulating the whole assimilation with a machine learning model. But people have tried model surrogates. So I've given references here. You can go back to this later on. So what we tried was kind of simple convolutional neural network be trained to emulate the traditional Kalman filter approach. And can this be augmented with the Kalman filter to do assimilation of high resolution data? The model we used here was a simple model, the Lorentz model, but this is the Lorentz 96 model, not the Lorentz 63 model. So this is solving a set of equations. Typically, it's 40 different equations with the exact same form of the equation. So you have coupling between the different variables, and it's typically representing a latitude ring around the globe. And if you integrate the model forward in time, you see these waves propagating through the model. So it's essentially representing the atmospheric like advection, atmospheric dynamics in a very simple setup. So we took this and we tried using the machine learning method to emulate BA in this system. The input to the machine learning was the forecast mean, the innovation, which is the observation minus the model observation, and then the forecast standard deviation, which is uncertainty in the forecast. And then that runs through this convolutional neural network, and it gives us an analysis mean, which is what the x tilde t plus delta t was in Sarah's talk. And it also gives an analysis standard deviation, which is the square root of the p, for instance. So we can train to replicate an ensemble Kalman filter analysis for this. And we did 3 different experiments. One where the ensemble Kalman filter is assimilating everything. So what we had was high resolution observation, so observing all the variables along the ring, and then a low resolution observation where we sample only every 4th variable. So it's like thinking of the satellite observing everywhere on the globe versus only sparse observations. So in the ensemble Kalman filter, one, we do all the observations. Another one, we only assimilate the low resolution. And another one, we do the high resolution observation assimilation with the machine learning, and the low resolution with ensemble Kalman filter. And what we get from this, what's plotted here is the analysis root mean square error versus time. This is the training period where Luke trains the model, gets the CNN or the machine learning model to be optimized. And then we can do a validation where we are running the assimilation. This is the assimilation of all observations with the ensemble Kalman filter, which is computationally expensive. This is the hybrid or the augmented method where the high resolution observations are assimilated with the machine learning and the low resolution is ensemble Kalman filter. And here we are only using the ensemble Kalman filter with the low resolution data. And what we get is that when we assimilate everything with the ensemble Kalman filter, it's hard to beat that. But the augmented method beats the low resolution observation. So practically, this is what is feasible. This one is computationally too expensive in some cases. Like I mentioned, if you have high resolution satellite data, we cannot assimilate all of that. But we could achieve machine learning emulation of your data assimilation and augment that to get a better estimate or a lower root mean square error. And then this is the error distribution. They look about similar. It's Gaussian in terms of the error distribution. And then we run forecasts from these initial conditions. So we do the assimilation and we run forecasts forward in model 10 days of the model. And here the error is plotted in the continuous lines. And then the standard deviation is plotted in the dashed lines. What we see here is that the error is the least for the case where you're assimilating everything with the ensemble Kalman filter. But when you do the augmented method, machine learning plus Kalman filter, the error is lower than the low resolution Kalman filter. And at long lead times, it's potentially more reliable also that the error is closer to, the standard deviation is closer to the error when you do the augmentation. Yeah, so this is the reference. You can scan the QR code at home to get the paper. Yeah, I can go into the stochastic parameterization and finish in 5 minutes, and then we have 5 to 6 minutes for Q&A. So in terms of the stochastic parameterization, like I was answering to Mikhail's question, what is typically done is you do a multiplicative noise term. So for instance, if you have a physics tendency, that's a collection of all the different physics schemes in the model, like the atmosphere, it could be cloud physics, radiation, gravity wave. So that gives you a tendency, which is d by dt of that term, temperature or humidity. You do 1 plus a random noise times this physics tendency. So you're saying you know that tendency, but there is an error in that tendency. So you want to sample around that value. So that's one representation of model uncertainty in the system. Another one is called stochastic kinetic energy backscatter. So if you have taken classes in turbulence, ocean turbulence or GFD turbulence, you know that there is energy cascade downscale, but sometimes there is also energy cascade upscale, that small scales transport energy to the large scale. But this is not represented in the real atmospheric or oceanic model. Most of the energy is dissipated past the resolution of the model. So yeah, folks, I think primarily in the UK, came up with methods of stochastically putting some of that energy back into the larger scale. So it's called stochastic kinetic energy backscatter, where you're scattering some of that energy upscale into the larger scales. I'll not talk about this today. So in the context of the ocean, one example that has tried this, in the ocean, one of the subgrid scale processes that is not represented both in weather or in climate models is eddies. With eddies there can be scales of like 50 to 10 kilometers, whereas the usual grids of the ocean models are 100 kilometers, 50 kilometers. So a lot of times the eddies are not represented, and eddies cause a lot of mixing in the ocean, right? So there is like a parameterization called the Gent-McWilliams parameterization, which parameterizes some of that. I'll skip this. Parameterizes some of that eddy mixing in the ocean. But previously, before this paper came out, that was a deterministic parameterization. There would be a fixed amount of mixing, fixed amount of what's called as a bolus velocity that leads to that mixing from the Gent-McWilliams scheme. So this is a reference where they try to have stochastic perturbations to some of the parameters within that Gent-McWilliams parameterization. I'll not go into the details, but what this is showing is the overturning circulation with the deterministic Gent-McWilliams GM scheme. So that's showing the North Atlantic AMOC, the North Atlantic meridional overturning circulation. And this is showing like the standard deviation when you add the stochastic perturbations. This is without stochastic perturbations. So they see that on the intraannual time scale, you get up to like 10 times more intraannual variability in the AMOC, even though the perturbations were added on a seasonal to lower, higher frequency time scale. So you give this high frequency perturbations, but there is nonlinear rectification that changes the long-term variability in the system as well. And it improves the model closer to what the observation is. Yeah, and then one quick example of machine learning for doing this stochastic parameterization. This work was led by David John Gagne, who's a machine learning expert at NSAR. So here we go back to the Lorentz model, but here we have a two-layer Lorentz system. So the first layer, you can think of it as similar to the Lorentz model that I gave in the data assimilation example. So you have this dx by dt equation, but now you have an additional term that couples this to the outer ring. So you can think of this as for the outer ring is like high frequency variability or eddies in the system. And then the inner ring is the large scale in your real system. So large scale ocean model at 100 kilometers. And then the outer ring is solving the eddies in the equation. So you have an equation for y, which then couples to the x equation. And typically solving for the y equation or the high resolution is expensive. So all of this can be parameterized as subgrid scale tendency that changes x, right? So what we tried for this was to use what's called as generative adversarial networks, which generate, which is a machine learning method that can generate terms or generate images, for instance. And the simple idea is it has two different neural networks. One is called the generator, which creates synthetic samples drawn from training data based on a latent vector, or a small dimensional representation. And then it generates like a synthetic sample of ratatouille, for instance. And then you have what's called as a critic, which determines which samples are real and which are synthetic, right? And that the critic knows what's the true sample, and it provides feedback back to the generator network, and they are training each other basically. So the generator becomes more and more optimized, and it can provide synthetic samples that look very much like the true samples. So we use this to generate what are true subgrid scale tendencies. Essentially, you can keep training this to get what the subgrid scale tendency should be in that Lorentz system. And there's also an option to add noise within the GANs. So you can add noise within the neural network to sample uncertainty as well. So we sampled both white noise as well as red noise, which featured in Adam's talk in terms of their spectral characteristics. Yeah, I'll not go into details, but we sampled many different noise levels and white and red noise, but we can see this is root mean square error and spread. So you want the spread to be close to the root mean square error for reliable forecast. And this is what's called as Hellinger distance. It's essentially the distance between the PDF of the system. So this measures the climate of the system. How well is it representing the climate? Whereas this is telling us how well is the weather forecast in the system. And in both cases, the gray samples where you have small white noise added to the system within the GANs can get a very good representation or a low root mean square error, as well as a good small Hellinger distance where the PDFs are close to one another. Yeah, so with that, I'll end my talk.